Good morning. This is my clock, almost 8 o'clock, within a few seconds. Now it says 8 o'clock. And we're going to have a short lecture before the exam. Actually, my plan is 1 hour from now we'll take the break, 15 minutes, and then come back and I'll get you started on the exam. One of the things, though, I got to grab out of my backpack here that I just realized. These have been sitting outside my office since last Wednesday. And since I'm on the microphone, I'm just going to lay them up here. Those are the tables for the exam. If you already have one printed, don't take one. I don't know if anybody picked them up outside my office. Good. People called me. People don't read everything now, and none of you are here that were like that. Where are they? They've been in front of my office since Wednesday. I thought I put a message out on it, but I did, right? Yeah. There's so much information flow that everybody gives. Right now, I've got a car in getting worked on, and they've been texting me because I dropped it off last night, and they're going to probably hit me with some more info here. Although I already approved the first add-on expense. If any of you know what it's like to take your car and you got to keep agreeing step by step for the charges that are going to come at you. Okay, so the first thing I want to point out from the website is what did I add? I've been working hard, which is the reason why I didn't do any more grading, at getting Project 1 posted and updated. The zip package that goes with it will get put up hopefully later today. We'll talk briefly about that before we head off for the break. I have reworked it though, so it's not going to involve any C++ like I did last year. That was a fun experience. I've left all of that up there, and the installation instructions for that are all up there. It will involve Julia, but in a very moderate way, and everything that I put into the project is in sample notebooks in the zip package. So in this particular case, the old ones are up there, but they're going to have to be modified for this semester. There'll be a sample notebook in Python for all the problems, with the exception of the last problem, which is based on PyAudio Helper and doing real-time DSP right in Jupyter in Python. So that has a separate notebook. So that's 2 Python Jupyter Lab notebooks. And then there'll be a third notebook to go along with just one problem where you're going to be doing some speed of execution comparisons between Python and Julia. And that one will be mostly all intact. You'll just have to do a tiny bit. You'll, of course, have to run it. But that's the reason why, and I'm going to hit you hard on this right now, that's the reason why at the beginning of the semester we went through that whole process of getting Julia and Python and Jupyter Lab all congealed together, so when you launch it now, everything should just be there. You may have to check out your PyAudio Helper if you've never had to test it before, but the sample notebook also has the ability to test the notebook for the audio, and I'll do a demo of that sometime in the lecture of how that works. So hopefully you'll be able to cash in on all that work that you've already done. The homework set number 4 is now posted, and I've also laid out the dates for the remaining homework assignments. Why would I do that? It's because it's now pretty obvious that I've got to make sure I stay right on track, otherwise things will be crashing at the end. But in so doing, and what I say in the what's new here is we're going to move right into chapter 4 on sampling theory. We're not going to jump ahead to FFT and then come back. The project problem that I pulled off was FFT based. I still am passionate about the FFT, but I'm also very passionate about sampling theory and all the new things that you learn in this class for multi-rate that are not part of what you've already seen as an undergraduate. So we're just going to maintain continuity, and admittedly I found last fall when I jumped ahead to the FFT, there were things in the middle in that interim that were kind of left dangling a little bit, not badly, but this way we're just going to be following through with the program as it's written out. And I'm not going to intently study the calendar, but I just want to go look at, we're here on the 12th. What you're going to be starting to do now is you're going to be working homework, and this set number 4 is due on the 28th, but I also want you to be starting to look at the project and start, ramping onto that. So in our wonderful terminology from electrical engineering, parallel processing, that's what we have to do. I mutter that to myself all the time. Get up in the morning, I've got to do this in parallel with this, in parallel with that, because all those have to be done before I can leave the house, right? Anybody not do something like that? You can't truly do 3 things at once, but you can quickly switch and keep moving everything forward on your timeline. So I'm expecting that. I debated and I said, no, I'll push this out because I'm hopeful that people will start studying the project. And that's something you can do immediately, this weekend. And I want to at least introduce the first problem, and that's in Python, because that's something that's based on something we did weeks and weeks ago. You're going to now be implementing something in Python. And then it gets into multi-rate after that, but we'll get there. So then the other thing is I'm moving down into November, and I don't know why this doesn't say November. Maybe I'm not in November. Yeah. I'm looking at something on the top. I'm looking at the wrong thing. Okay. So November 18th is going to be another due date on another assignment, and there'll be another one in between that too. But that'll be the point that we'll pause again and take exam number 2 as a take-home, which will be due on the 22nd. The project is nominally due on the 22nd, and we'll be discussing that on and off between now and November 22nd. And then we come back from the Thanksgiving break, which is Wednesday, Thursday, and Friday of that week, last weekend, full week of November. And then I'll have shorter length assignments due on December 2nd and December 9th. And then we'll be lined up for December 16th, or 14th, for the final exam. And the project will be due then too. I don't like looking at things like that because I got so much to do with so many students and cleaning out my office. I'm overwhelmed just even thinking about it. But every now and then you got to just sort of poke something in your brain, and hopefully you can remember not to forget everything, because it's not going to be very pretty looking if we don't keep thinking about what lies ahead. Okay, so going back over to chapter 3, one of the things I did not do that I promised you I would do, I wanted to look across the transform properties of which you've already utilized in that homework set number 3, and go prove at least one property that you used, but I just want to prove it using one of the theorems that's in here. So linearity we started using immediately when we were transforming. Remember, we did 2 exponential sequences, and then we utilized, get my pen working correctly again. Immediately started utilizing that the region of convergence is the intersection when you have a linear combination of 2 functions. Time shifting, we bumped into, this is the formal statement of this. I think I talked about this last week. The simplest form of this is the z to the minus 1, which shows up in block diagrams that we'll be using, and signal flow graphs that we'll be getting into eventually. But whenever you see that z to the minus 1, we just use that notation to say that the signal gets delayed by 1 sample. And you'll be utilizing that a lot. It shows up in the project in a topic called polyphase filters, which is one of the problems, and it's a topic that's embedded in chapter 4. I plugged an example in here using the delay theorem. This is kind of a cool little example. When you work the exam today, if you see an opportunity where you see, say, a z to the minus 1 or z to the minus 2 or something, and I'm not even thinking if that shows up at all, but if it does, you get your option of just pulling that z to the minus 1 outside, inverse transforming what remains, and then time shifting everything, in this case, by one sample. So this problem, this example is a good one because it shows you how you would do this directly. You'd have to do long division, let's say, unless you wanted to prove it just from the definition, which is always an option too. But here I did long division and then inverse transform term by term. But down here, this is the beauty of using the theorems to your advantage, is just say, okay, there's a z to the minus 1 that I can pull outside. That means that there's a inherent one sample delay that's going to be present when I get done with what's inside the braces. So just apply n minus 1 in place of n everywhere. And I think you probably know already that from working the homework problems and maybe comparing solutions that are in the back of the book, that when you say use the delay theorem, or here we just did it the long way, the two forms might not look like they're the same, but when you look more carefully, you can see that in this case that 4 times 1/4 to the n can be written as 1/4 to the n minus 1. So that minus 1 on the 1/4 is the same as 4, right? It's not an issue on the exam today because you're not going to be going backwards and forwards, say, oh, did these match up? You're only going to pretty much have enough time to work it one way, but it's just something that is nice to know. Multiplying by an exponential, it's kind of an exotic theorem. I'm not going to review that one. Differentiation theorem is useful in some rare instances, and one instance is an example that I have in here. What it's telling you, though, is the theorem straight away just says that if you multiply a sequence times n, this is, in the z domain, equivalent to multiplying by minus z and then the derivative of x of z dz. This should kind of seem familiar to you because if you remember in the Laplace domain, if you had t times some time domain function, that would show up as a derivative in the S domain. I don't know if you remember that at all, vaguely. I mean, I'm not insisting on this, but I'm just saying there's a connection in there. The thing about all these theorems, though, is the region of convergence doesn't necessarily carry forward without some exception. So in this case, what happens is it's possible after you take the derivative, and then you also have this term right in here, that's going to, a positive power of z is going to go to infinity at z, magnitude of z going to infinity, and that means you have to exclude that from the region of convergence. Or possibly if there were some other negative powers of z, they would dominate and you'd end up with a negative power z, which means you could not go to 0. This is just the proof of the theorem. And there is one proof type problem on the exam. It's not rigorous, but you'll see it. Hopefully your brain will tune in and you'll say, I got it. I'll figure this out, because nothing's that hard. In retrospect, it's always harder when you're in the situation, though, right? So you'll find out more later. So here's the example that I wanted to spend a bit of time on. This one just says if we have n times a to the n u of n, what is its z transform? So this is just kind of a hypothetical who would pick this, but it's interesting because it's going to lead to something that's going to allow us to get a proof of something that was a given last week. So we go ahead and plug into the theorem on the right-hand side and take minus z times d dz. We have a quotient rule there from calculus, so we get the derivative of the denominator times the numerator, and then we get plus the derivative of the numerator times the denominator, and then we get the square of the denominator from the quotient formula from calculus. We only get one term though, because d, the derivative of the constant, is 0. So on the numerator side we get a times e to the minus 1, and then we have in the denominator that quantity squared. And then we also have, let's see, let me just write this out right, since I make sure I'm awake on this. So we take the derivative of that with respect to z, and we're going to get minus az to the minus 2, but then there's this minus z sitting over here, so when you put the minus z times that, that's where the az to the minus 1 comes from. Good with that on the quotient formula. Do you ever think you were going to forget that? I mean, I'm just questioning you because I oftentimes, on more involved theorems in calculus, sometimes you have to go take a look at some notes for calculus. So now that we have this, the question is, can we use that to get at another theorem? And I put that, I already embedded that in here this morning. So I created this Scratch document this morning where I took from earlier in chapter 3, I said this is how you're going to inverse transform a double pole term. Remember, you'd have an AK sitting on the top, or CK, whatever it happened to be, and you'd have a second degree pole, and said that that would be n plus 1 times a to the nu of n. So now what we've just done here is we've just established this from the differentiation theorem for z transforms. So now we can go back up to this using some other properties of z transform. So what shall we do? This would be a good exam question. It's not on the exam, sorry to say, but it's a good example of what you can do. So you look at that. What we'd like to be able to do is we'd like to be able to take what's in the red box right now and make it into what's up on the top side there. So what can we do? I would start on the z domain side and say, okay, I want to get rid of So I want to remove the a times z to the minus 1. So what happens if I do that? I'm going to get 1 over a. I can move the constant from linearity to the other side of the z transform pair. And then if I take away a z to the minus 1, what is that going to do to the time shift? Remember, we just talked about the time delay theorem. One sample, n gets replaced by n minus 1. So now if we remove a z to the minus 1, what's going to go on? N is going to get replaced by, I'm checking to see if you're thinking, if we did replaced n by n minus 1 when we included z to the minus 1, when we take it away, n should get replaced by n plus 1, right? So rather than the sequence shifting to the right, it's now going to shift back to the left by one sample. Yeah, make sense? Okay, so I just make that substitution. So everywhere in here, I replace n, and this is an important part of using any of these theorems. You've got to be consistent. So now we have that, and then I can start simplifying. Oops, I wanted to change the blue. So if I divide through by a, I'm going to get rid of that a to the 1. That's going to be gone. And then we're left with n plus 1 times a to the n So now we look at that and we say this and up in the upper left, they're supposed to be the same, are they? So a little inspection now is required. U of n plus 1 is a step function that starts at n is equal to minus 1. At n is equal to minus 1, notice that if I put minus 1 in here, that term is gone. So it annihilates itself when n is equal to minus 1. So we can just rewrite this as n plus 1 times a to the n u of n. Just say we start at n is equal to 0 because there's nothing present for n is equal to minus 1. Is that good? Just, is it trickery? No, it's just using the common sense, but okay, I didn't have to do any hard lifting. The hard lifting was actually done by the theorem, the differentiation theorem. But the other thing that the theorem had to do was, we had to be motivated by having this example written down. You had to be motivated and curious about what does n a to the n u of n transform to, and then it happens. And then, interestingly enough, the n plus 1 shows up in the solution. Remember I said that would be a little bit counterintuitive to what happens in the S domain. In the S domain, when you have a repeated pole, you get a t times e to the minus at. We're not getting the equivalent of t you would think would be n, right? Because that's our time index. But instead it's n plus 1. It's just one of those slight differences between continuous time and discrete time. We just have to accept that fact. It starts right away at n is equal to 0 with 1 rather than 0 in the continuous time case. That's how I look at it. I mean, I've come to accept that, but I've been looking at this for quite a few years. So, okay, moving onward, we talked about the convolution theorem. There's examples with that. Then this contour integration section was just bonus material for some time later in your life if you get inspired. I'm saying that because you may never be inspired to look further, but it's there. Or you might be reading a paper or another book for something involving a work type problem, and you might see contour integration. So it might inspire you to either study these notes or find another book that still uses contour integration. So the last thing out of this chapter that I want to briefly look at is the unilateral Z-transform. I don't have any homework problems on it. I've never done an exam problem on it, but I want to at least talk about it briefly because it is closure on the Laplace transform that you already learned for solving boundary value problems or initial condition problems in circuits. Remember, or maybe you don't want to remember, but what I remember from my days in circuits was I was okay with DC circuits. I was okay with sinusoidal steady state, AC circuit analysis. When it came to transient circuit analysis and writing out the differential equations, I just wasn't particularly in love with that. It was tedious, kind of messy, and then you get introduced to the use of the Laplace transform, and then you say, well, it's not too bad. I just have to add in some more rules, remember, for transient responses in the S domain, and then you can get by and you can do circuit modeling in the time domain. But in reality, if I have to do circuit modeling in the time domain and I want a quick answer, I'm probably going to go to LT Spice or something like that just to get up and running with something. If I need to delve into it more theoretically, I will go off and do that after, because I'm more of an after person than a before. I learn my stuff, but I want to make something work as soon as possible, and I want to see it in a tool if possible, because that's a more contemporary way of doing things. It's not an excuse for not making your brain work, though. It's just saying get your feet on the ground and then you can study the math part of it. So the unilateral Z transform does that in the discrete time domain. It's different from the bilateral case because now this sum is starting at 0. So it's going to ignore anything in the signal x of n for n less than 0, which is generally exactly what we want. We're going to assume that no signals are applied until n is equal to 0 and carry forward from there. The unilateral transform always deals with right-sided sequences, so the region of convergence is always the exterior of a circle of the maximum pole radius. And you could just kind of forget about that in reality, because if you're dealing with a causal system, you're also thinking about stability as meaning that all the poles lie inside the unit circle. Just like when you studied the S domain, you didn't worry about the ROC even though it existed, because there you were also thinking about stable systems that are causal where all the poles lie in the left half plane, right? So now you're also seeing, so that's why they never had to tell me these things, because they were keeping you in the dark. It was just like, you won't care because you're doing, unilateral analysis and you're dealing with causal type signals. But remember, the Z domain is more powerful because we can run things backwards. We can do something crazy that I was bouncing into when I was working on the project yesterday. There's a function called filtFilt that's available in MATLAB, Python, and Julia. What does filtFilt do? It takes a finite length signal, runs it through a filter, so it wraps phase and amplitude response onto it, like we learned about in chapter 2. And then it takes that entire array, spins it around, sends it through the filter a second time. So it wraps phase in the opposite direction on a second time, and it wraps amplitude response on a second time. So it comes out with 0 phase, but double the amplitude response. So if it was a third 3-pole filter, it would now be a 6-pole filter, because we'd be cascading the magnitude response. However, that doesn't make any sense for a real-time processing system. You're not going to wait for the end of the vector in a real-time system because it's never going to come, right? Signals just keep coming at you. You can't say, let me stop, let me flip it over and send it through again. But you can do that in a data processing sense, and it certainly is done. Machine learning people are probably, that want to do some processing of a time series, might say they want to do something like that because they just capture a certain time series. They want to manipulate something with it, like maybe do speech recognition or something like that, looking for patterns, identifying speech patterns and things. My brain is wired to the idea that I'm working on a SATCOM system or some comm link where the data just keeps flying at me and I have to just do it and I don't get a chance to back up and flip something around. So at any rate, if we want to compare the unilateral and the bilateral, they're the same. If the delay theorem works out the same, as long as n naught is greater than or equal to 0. The theorem works out the same. If the sequence is got n naught less than 0, then it doesn't apply, but we're mostly interested in having it apply. So in the notes here and in the book, it talks about time shifting property, and it's always going to consider two different cases, n naught greater than or equal to 0, and then n naught less than 0. Mostly interested here in just n naught greater than or equal to 0. So what you get is the standard Z transform result from the two-sided case plus an additional term. That's like an add-on term that comes along for, wait a minute, I got this backwards. We expect this term from the two-sided case. We take a signal that's getting delayed by n naught samples and then multiply it by the Z transform of the waveform. But the first term there is the one that represents all the terms for n less than 0 that are coming through. So what would happen is if the signal comes in like this, so what happens is after you delay it, change the color here. So since the one-sided Z transform can't see anything for n less than 0, what happens if we delay a signal by positive value n naught, some of the things in that blue hashed area are now going to move into the field of view of the one-sided transform, and they're going to become a little interval that runs from 0 up to n naught, and that is what this first term is over here. It's those signals that were not present, or samples that were not present in the original one-sided Z transform of X because they were out of the field of view. Now that they moved in, we include them, and then the rest is taken care of by the one-sided Z transform multiplying by Z to the minus n naught. So if we look at this as a summary, what it looks like we've got is we've got all of the terms for n less than 0 are being included up front over here. You think of those as initial condition terms. Notice there's x at minus 1, x at minus 2, so on backwards in time. And then the one-sided Z transform of all those terms for n greater than or equal to 0. So what should be hitting you right now is you should be saying, oh, so that's how we're going to be able to incorporate initial conditions into the Z transform, by having this one-sided form, and then the initial condition terms get included separately from the other terms that we're more used to seeing. So when you want to go solve a difference equation like right here, like we did way back in chapter 2, we're going to have a generalized type of initial conditions. We're going to have values like this present on the output if we needed them, and then values from the input if we needed them. I mean, all these would be the states in the system of how it was when we started it up. I realize in circuits you think mostly of what is the charge on a capacitor, what is the current through an inductor, and those are instantaneous at t minus, right? Remember from circuits it was always what was going on at or zero minus, zero minus just before time zero occurs. So in the discrete time domain that expands because of the discrete nature of things into a collection of state information for the output and the input, telling us how non-zero values can be incorporated into our solution. If it was an impulse response we were going after, or we were assuming the system was at rest, then nothing, those would all be zero terms. But this is where we can include the non-zero values. Like, I'll take Kaylee as an example since you're working on battery stuff, right? There's a state of charge in the battery pack. When you start it up, if you stop using it and start using it again for another experiment, it's got a different state of charge. Or if you're, I'll use another weird example, but it's a controls example. A freighter is going through the ocean and it's got its rudder set not at 0 degrees, but it's at like plus or minus 5 degrees, let's say, because it's in the midst of making a maneuver in the seas. If you were modeling what's going to happen when you start the system up, the rudder's already been turned, so that forms a state, and now that enters into the solution because you've already had a state going, and there'd be some additional states that would go along with that because there's, in my mind, I took statics and dynamics for mechanical. You guys, if you didn't take either of those, you just have your mechanics from physics, right? But you know that there's a body in motion is not just its position, its velocity, its acceleration. So those things would enter into additional components, which in the discrete time domain model would be those extra states there, representing the fact that there's a mass going over water and so on. Am I good at that anymore? No, but I took the class and it was very much like circuits, except it was all mechanics. It was all moments and things, moments of inertia and things like that, whereas EEs work with the circuit elements. So when you go to solve this difference equation using my mouse just died there for a second, using the one-sided Z transform, you end up wanting to, you end up taking the unilateral Z transform on both sides of the difference equation, and you end up with, say for the output side, you end up with the Z transform y of the output y of Z using this calligraphy y to represent a one-sided, but you just have the coefficients directly incorporated there. This is just like what we'd have with the two-sided transform, but then this second term is the one that incorporates the initial states, the values of the output for n less than 0. That becomes yi, or y initial condition on Z. And then you do the same thing on the right-hand side. You get the standard one-sided Z transform like the two-sided for the coefficients, BR, and then you have the term that involves the initial conditions on the input, the initial states of the input signal. And then you formulate that together so you can solve for y of Z in terms of everything else. And then you get this term, this is from before, that is, it's going to be x of Z one-sided times h of Z. And that just carries through from before, assuming the one-sided Z transform is taken there to represent x of Z, and then you get two other terms. You get a subtraction term from the initial states on the output, solving that out using partial fraction expansion, let's say, and then you get an addition of the initial states on the input with the denominator from your h of z, and then you solve that out using partial fraction expansion. It's messy looking, and that's probably the reason why I've never wanted to do. I have a very simple example in here, but in general, though, it can be done. And because of residue z, you should not be that fearful that you can't approach something, because you have a tool to help you with the partial fraction expansion if you want to go that way. So the only example I took in here was just a single system like we did back in chapter 2. Y is equal to, well, the impulse response is a to the n u of n in this case, remember. And assume that the only initial condition that's present is going to be the output value at -1 is c, because that's what we did back in chapter 2. Then take the unilateral z transform of both sides, put it together, and driving it with a step function in this case. So we're driving it with a step function, which would be, that would be its z transform. So the forced response is going to be the step function z transform times the system h of z, or system function h of z. So this is forced response that contains both a steady state and it also contains a transient. Just by forcing the step function in, it excites the system, it sets it off, heading to a steady state answer, but there's also going to be a decay of the natural response, and that will be due to this pole, right? That's the pole, oh no, yeah, this is the pole of the system, and so when that gets excited by the step, it creates a transient, a to the n u of n, but that's going to decay away in time. The very first term, though, is the initial condition related response. It's not my car, it's my eyes. My eye doctor sends me reminders too, right? You probably have the same thing. Go in and have your test. Okay. So there's where C shows up, that's the initial condition, and that's going to have the a to the n u of n response from the initial state, and that will, of course, join forces with the partial fraction expansion of this term and be another component of that, just from the forced response. Does this all sound reasonable? I'm not making you do anything with it, I just wanted you to know this. It's kind of like, just in case you ever need it, it'll be here. And this answer down here is exactly what we did before. And then I carried it forward into the Python discussion with using initial conditions in Python's L filter function. So I set an initial condition in there. I set zi equal to -1 times 0.8, and that was just going through I went through the math up above, and then when it runs out down here, you can see that the step turned on at 5, but starting at 0, there was a rundown of the initial condition that was in the system when it started, and then the step response formally begins, but the initial condition is still embedded inside of there. It's still running out over time, and decaying to 0, of course, too. Any questions on that? Does this fact, I'm just curious, Kaylee, since you're working with the battery control lab, everything you do for controllers is discrete time domain, right? So is this, could this maybe be a part of something that goes on over there? I mean, I'm on the dissertation defenses frequently, not anymore though, I'm done with that, but I have been from those two faculty members, Platt and Trimboli, over the years. I think it's nice to know, probably more from a control system standpoint than anything else. So now what I'm going to do is give you a quick tour of the project. I'm also just going to point out that in set number 4, if you want to get started on it, the first few problems are simple sampling theory problems, but they're in a different context, so you have to be rigorous on these. You can't just say, oh, the answers are in the back of the book. I would need to see the steps at all times. And then I've got bonus problems on a couple of these. This one is fairly intense to prove it and go through it graphically. The hints page will help out a lot when I get that out there. This one involves some calculus and integration type stuff that's a little bit tedious too, so that's why that one is a bonus problem. 430 is just kind of long-winded, and you'll be drawing sketches of in a multi-rate sampling system. So that'll be one of the new things that comes along in this assignment. Okay, a quick tour of the project. It used to say Python/C++, now it says Python/Julia. I've taken the C++ part out. No fears though, if you would like to explore it sometime before the end of the semester, because I don't know where the website's going to go. Hopefully I'll know where it's going to go before the end though. What I did is I broke the Python projects tab down into a fall 2022, and remember it's likely, it's essentially assured that this GPS project will get tweaked a bit and it will be used for project number 2, the GPS synchronization. It's a pretty straightforward canned project, not really much coding, just following directions and running some experiments. That one will get reissued and show up above here, but I'm leaving the old 1P and the adaptive filters problem 2, project 2P up here just for good old time's sake. And what I have to do is I have to add the zip package in here, because the zip package that's in here is no longer appropriate. I have to redo it slightly. And I'll probably hopefully work on that later today. So that's what I was starting to look at over here. So this is treated as a take-home exam. Each student has to do their own work. The exception being to this honor code, essentially, is that I will allow you to work in teams of, if desired, if you're taking this as 4650, which is many of you. An undergraduate can't work with a graduate student, though, because they're under the rule of they have to work by themselves. But if you're both undergraduate students, then you can work together on the project. Does that sound reasonable? You can tackle the problems however you wish. You can say, I'm going to try this one. I'm going to try this one too because I'm having problems. And then you can divide and conquer on some of the other problems. It's going to be kind of up to you. And if you're just stubborn and want to work by yourself all the way through, go for it. Mostly the graduate students enjoy working by themselves anyway, and they don't really want to be attached to a teammate. And I want them to do it by themselves anyway. So the rest of the top here just talks about what I wanted you to have installed from your Python Julia setup. Everything should be good to go to do all of this if you succeeded with that, but there'll be some verification. So there's 5 problems. First one you can start on after the exam today if you want to. Multi-rate sampling theory will require us getting there hopefully by next Wednesday. Polyphase decimation in Python, and then in Julia that will require chapter 4. You can though you can start the notch filter investigation, which is the same notch filter that I've talked about and demoed last week. You can also do parts of the real-time DSP using Pi Audio. You can start some of those at any time. I'd recommend starting on the very first problem, because if you haven't spent enough time getting into programming in Python, and you could do this in Julia if you want to, but I'm already seeing most everybody is wanting to use Python, which is fine. Start on this because this is more of a programming exercise. What you're going to do is you're going to develop some code that will handle initial conditions, what we just came from talking about. So you're going to write simulation code for a discrete time difference equation solver that will get the output here in terms of the input, and then the possibility of having initial values on y, so like y minus 1, minus 2, and so on, and x at minus 1, minus 2, and so on. So you can see this is in the Jupyter Notebook sample that'll come out. You get to load in an array that contains the initial conditions, and I give you some test vectors in here. And I talk about how to write the code too. I give you some test vectors in here, and I think the test vectors are in the notebook, so they're not listed right here, but the test vectors are defined in the notebook of what you're going to test it with. And then you're going to time the code too using time it, which is talked about in problem number 3 again. Multi-rate problem, so we'll get more into that eventually here once we get into chapter 4. Polyphase decimator investigation with a test vector defined. This is all set up in the notebook. So what is a decimator? We're going to learn about it. It's a low-pass filter followed by a downsampler, reducing the sampling rate. And the low-pass filter is basically there to make sure there's no aliasing in the signal once it gets downsampled. Because if we originally sampled the waveform at a lower sampling rate, that means its requirements for aliasing would be stronger than if we sample at the higher rate. So the low-pass filter there is a protection filter to keep aliasing from happening. But the whole idea of this we'll learn about is, as we move into the chapter 4, is that if you low-pass filter at this higher sampling rate and spend all that work, and then you come along in here with your downsampler, and the downsampler is only going to keep every nth sample of that filter output, you're doing a lot of extra calculations only to throw those samples away. So the polyphase idea is what people use. And by the way, decimator, I'll talk more about this when we get into the lecture, but if you have a military background, what does decimate mean? Okay, so in an army scenario, what would that mean if you decimated the army? I mean, I'm just thinking back if you read a novel on, we decimated the enemy, what would that mean?
Nothing good for the enemy.
So 1 out of 10 survives, right? I mean, that sounds cruel, but so why did DSP pick up on this term? Because it kind of looks like that mathematically, but in terms of human, body count, it's not a good thing. But engineers are good about kind of being right in your face with the terminology, though. I'd been teaching on this for a long time, and then I looked it up in the dictionary. I said, what does the dictionary say? And it says exactly what you just said. So the polyphase idea, though, says that you can move the filters after the downsampler, and that's where the efficiency comes in. But writing code to do that is kind of another matter. It's very easy to write an algorithm and have it run slower than another algorithm, even though you think you're going to be able to get away with something. So it's going to be hard to get it to run fast in Python, and I'll explain more about that later. The notch filter problem is pretty straightforward, and then there's a whole array of problems using Pi Audio Helper. So I'm going to just move on from there and use about 5 minutes to just introduce sampling of continuous time signals. If I was you and I was taking this class, I would in the end, I would say this should be the most exciting chapter, because it's really hands-on about what do we do in modern DSP that we didn't do, so much of 20 or 30 years ago when it first came into being. We do multi-rate sampling, and to get introduced to that, we have to just talk about the basic, what is continuous, what is a DSP I/O system look like. So a DSP I/O system takes in samples in the analog domain. At some point, you may never see that in the work that you do, but somewhere in your system there is some A to D, and then it frequently goes back out again. It doesn't have to, it just might be analyzed, so it might be split down the middle, but this shows an I/O system. If you're thinking about listening to music on the internet, streaming it, you just have the back end of this, right? You just stream the data bits, and the DSP processor has to do some decompressing if it's compressed audio, and then eventually go to a D to A and then have a reconstruction filter. But this is kind of like the full-op system, and those of you taking the lab, this is exactly what the lab system is doing. You have an A to D and you have a D to A, and you actually have 2 channels, right? You have a stereo system. So I've just depicted this with anti-aliasing filter, which eliminates some higher order harmonic components. So it takes a square wave and makes it look like it's got ringing, because that's just representing the band limiting. And then I've tried to show, it's kind of hard to see on here, but I'm showing these as being after the sample and hold, there's now stair steps there. The analog signal gets sampled after the anti-aliasing filter, but the sample and hold is going to hold it while the A to D converter goes through its conversion cycle. Explicitly, the sample and hold might be built into the A to D, so you never really see this, but that is kind of the notion of what's going on. It takes a bit of time. A flash converter can do that instantly. Sigma delta has to converge, and successive approximation A to Ds, which MSP 430, you all worked with that if you were here at UCCS. Remember what did the MSP 430 have on it, or 432 I guess you were using. It probably had 2 A to Ds on it if I'm remembering right. It has one that's a SAR, successive approximation, and I think another one might be a sigma delta. I don't really remember exactly. I was involved in picking those subsystems out quite a few years ago, but if you have a Raspberry Pi, what converters does it have? Most microcontrollers have 1 or more types of A to Ds and perhaps D to As on them. At any rate, that's where sample and hold would come in. You have this idea of the successive approximation, which I'll probably talk about later. So then you have a bit stream, so I'm just showing vertically down there binary words which represent each sample. So like in the DSP lab, it's a 16-bit signed integer, so there's 16 bits included, usually in a 2's complement storage format. DSP processor takes those samples that are in, say, int 16t, which is the standard notation for signed integers that we use, and modifies them with some algorithm. And then the D to A converter takes the signed integers and converts them back out to analog samples, but the analog samples have a stair-step approximation, because every time the A to D converter writes, it puts out a fixed voltage, it holds it till the next sample, and then it switches to another one, and so on. And then the reconstruction filter cleans that up, so we'll be looking at all those steps all the way through the chain. Since I like hardware and I like seeing things really happen, every one of these steps means something to me. Mostly in this class is just the math modeling on the interior side of things, but we still think about what's going on. And the starting point is periodic sampling, which I'm now going to have to stop at, but we're going to be modeling periodic sampling using an ideal sampler, impulse train sampling, and then we'll switch to the frequency domain so we can get the alias spectra and all that other cool stuff. And weeks ago I talked about continuous time Fourier transform review, so that's right in here too with these theorems. Too much stuff to talk about. I have to stop. My wife says I never stop talking, so I have to stop. Let you have the break. If you've got any last minute questions on your way out to take your break, you can stop and talk with me. I'm probably going to be working on getting up a demo for Lab 4 and maybe grading some homeworks on my tablet, depending upon what I'm the most excited about doing. But be back here by quarter after. I've got the exams here ready to hand out, and those study formula sheets are down here. A lot of you walked in late, but they're sitting right down here. If you need one of those, it's here. The ones that were outside my office. So I'm going to stop the recording for the day.